Hello students, and here we are in the automotive studios to learn about the Ford 10R and the GM 10L80 gear set and mechanical and hydraulic operation. Let's get to it then. In this lesson, we're going to go through and look at the range reference chart. We're going to go through the gear set and clutch layout. Brace yourself. We're going to cover power flow. It's going to clear your mind when we go through that. Hydraulic system, we're going to be building off of what you guys learned in your previous transmission. So we'll be looking at the line pressure control, torque converter control, and how they control these clutches. You're going to find the system is pretty simple, pretty straightforward. It's a nice transmission, except for a few little quirks, but we'll get into that. And we'll talk a little bit about the fluid level and type, kind of the maintenance side of things. And to start out with, we'll look at this range reference chart. If you remember, a range reference chart is going to show you all the different gears available along the side, all the clutches that we've got up top, and it's going to tell you which clutches are applied and when. Now this chart right here is derived from the dyno experiment that I did on the Trail Boss, on the dyno. And the reason why I mention that is because it's actually different than what they've got published. So I don't know what's going on, if it's a little bit different in real life, or if this is just a one-off thing that this vehicle does, where these asterisks are. When we look at the actual hydraulic, the clutch pressures, they're there. There's a little bit of pressure, but it's not like full line pressure or the maximum pressure that you would expect to see. They might be a third or half of what it is. Now, everywhere where you see A, that just means the clutch is applied. Now, our brake clutches are clutch A and B, meaning those would, when they're applying, they're holding a component to the case. The B also kind of, it goes through and holds the same part that the one-way roller clutch does. One-way roller clutch and the B clutch are going to hold that sun gear, the P1 and P2 sun gears. And this is obviously going to only hold it in one direction, and then allow it to freewheel if it wants to in the other directions. Whereas the B clutch, when it applies, it's going to be able to hold that those two front sun gears stationary regardless. One thing that you might notice here is that there are, for the most part, 4 clutches applied in each gear. And, if you include the one-way roller clutch. So there's like 4 clutches, 4 clutches, 4, 4, 4, all the way down. So what they do when they're shifting is they're releasing a clutch, applying a clutch, and, in this case, the one-way roller, I guess the 2-3 shift, they don't really release a clutch. The one-way roller clutch just starts freewheeling. And then when you shift from 3rd to 4th, we release the E clutch and apply the F. 4th to 5th, we release the A clutch, or D clutch. A clutch, it says A there, got me. And apply the E clutch. And then in 6th gear, we release the C clutch and apply the D clutch. And yeah, you get it. That's kind of goes along down the row there. Now GM, as I've noticed on these dynos and driving these vehicles around, it likes to actually shift every gear. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and down 4th, or down shifts that same route. Now, if you look at HP tuners, if you look at that, they've got tables that show you skip shifting. So I guess you could probably do the skip shift if you want. Now Ford, they like to skip shift. They actually jump around quite a bit. And a lot of people, when they tune the Fords, they actually take that out. So maybe GM's just like, leave it out. Let it go through all the gears. You paid for them, you might as well use them. And this is the actual Ford published range reference chart. So I just put it up there for reference. Now it's not the actual Ford published one. I rewrote it. Hopefully I didn't make any mistakes there. One thing I also did is I put the gear ratio that they're operating at for all the different options. You can see it's got 3 overdrives, and direct drive is 7th gear. And then I also put the spread. So that's like the ratio spread. How much did the ratio change? You can see it's pretty close. The 1-2 shift is the greatest with 1.57, but most of these are, around 1.2. And that's actually a pretty good, tight spread. The reason why that's maybe desirable is because your engine RPM is going to drop about the same amount every time you upshift. So something to think about. That's why they got 10 of those gears. This little homemade drawing could probably bend your brain, make it hurt a little bit. And those of you that have gone through, some of the other sections in this class, you will recognize this. This is a block layout of the whole transmission. It's going to help us understand it. As long as you follow through and you understand how it's put together, this allows you to take all those parts that are sitting inside this shell that you can't see, and it's going to make it so that way we can maybe understand how this is laid out. Now, disclaimer, this is not laid out exactly how it is in the transmission. I changed it around so it'd be easier to draw. So let me explain what we're looking at here. We actually have all 6 clutches here and a roller clutch. So that's the one-way roller clutch, and that is the B clutch, A clutch, this is the F clutch, that's the C, that's the D, and that's the E clutch. And I'll show that to you here in a second. And then these are the planetary gear sets. So this is actually planetary gear set 1. That would be the ring gear, carrier, sun gear, the other half of the carrier, the other half of the ring gear. It's almost like it took a bandsaw and slips and sliced that transmission right in half. And then you're looking at like the cross section of it. This would be P2 gear set right here. And that would be the ring gear, carrier, sun gear, carrier, ring gear. So boom, P2. Way back here, P3, ring, carrier, sun, carrier, ring. Did I say P2? P3. And this is P4. Ring gear, carrier, sun gear, ring gear. And this is the output shaft. So we have 4 planetary gear sets. 1, 2, 3, 4. And our 6 clutches and our one-way roller clutch. Now if you notice, I also kind of try to keep the color schemes together. So this orange color, these are all things that are connected to the P1, planetary 1, first gear set, and P2, sun gears. So those are all connected to that P1 and P2. And everything in red is part of the input shaft. You can see spline to the input shaft is the carrier. You might remember that. We've gone through this already. There you go. And so this center section here is this internal gear, or ring gear. We like to call it a ring gear usually, but the P2 ring gear, and it goes all the way through and splines to the P3 sun gear. Ta-da. P2 ring, P3 sun. So I could lay it up there. Look at that, it's almost exactly the same size. Didn't even realize how good I was at drawing this. And then this is there's a little hub that's going to allow you to connect to the carrier. P3 carrier, the little hub that the clutches grab onto. That's the hub section right there. Those are the carrier gears. Right there. And then we have towards the back, the E clutch is inside this drum, and it is got the ring gear right there, sun gear on the back, so it's like, dang, look at the muscles. Don't be jealous, y'all. Don't be jealous. And right here is our output. This is our output gear set. Like that. Planetary gear set. So all the outputs come out of this planetary gear set right here. And kind of to cap it all off in green, going all the way from the front of the transmission, we've got a carrier, and then we have this shell. It goes all the way to the back, and that's where our ring gear is. So you can see it's like, boop, right there, and then spline to the shell would be that carrier. In there. So you can see this is all kind of a common connection. Don't worry about that. That part that you just heard was that sun gear. I didn't really show you, that's in orange. See, that's the common sun gear right there. So, like there. So this illustration here shows you all those parts. So after giving you the rundown, these are the actual slides. You can see I defined the 4 gear sets in this area, P1, P2, P3, P4. And when I say P1, I mean planetary gear set, not just the planetary carrier, but it's the whole thing. It's the ring gear, carrier, and sun gear. Ring gear, carrier, sun gear. Ring gear, carrier, sun gear, blah, blah, blah. Those are our clutches. They're labeled out there for us. Our one-way clutch, B clutch. You can see now what's happening here. Make the connections now. The one-way clutch has the ability of holding this P1 and P2 sun gear in the counterclockwise direction. And the B clutch, if it applies, it says, I can hold you in both directions. So if they need to hold in both directions, that's what the B clutch will be applied for. If it only needs to be held in the counterclockwise direction, that's what the one-way clutch is for. And then the A clutch, you can see is right here. It's between the K. So these two are our three really, are our holding clutches. So it's going to hold the P1 ring gear, keep it from spinning. Then we have our triple clutch housing, the infamous, at least as far as Ford is concerned, our infamous triple clutch housing. So on this side, we've got our C clutch. This side, we've got our D clutch. And then on the outside here, we've got our F clutch. You can see the bigger one is the C clutch, the outside one is the F clutch, and the small one is D clutch. That's how you remember it. The small one is D clutch. Get it? D clutch? Anyway. And then in the back, we've got our E clutch. And E clutch is, as I showed you earlier, located in this drum at the back. Got to take the snap ring out to get the drum off. And yeah, so that clutch is right here located in the back, and it's going to take the input shaft, lock it to that drum assembly. That drum contains that ring gear and that sun gear. So now, going through these common connections, these are going to show kind of the common parts, like this is connected to that. And right here is our input shaft. You've already seen this picture, and maybe it's starting to make sense. Everything in red is the input shaft. If it's in red, if one part's spinning and it's red on the other half, it's spinning too. So and this is that P2 carrier assembly. And so this is that whole assembly right there. So this is the input shaft. This is the P2 carrier. And then back here is now this has got the clutch in it. So it's, the clutch is splined to the input shaft. So if that clutch is applied, then it will drive that drum. Common connection there. Now I added the case. Got everything in white here is a transmission case. And then I added the common connection with our sun gear up front. See that? Sun gear. We've got the spline on the inside. That spline allows you to connect to that one-way roller clutch. And on the one-way roller clutch hub, there's a clutch pack assembly, the B clutch, that will hold this assembly. So then we have the ability of holding it in both directions with the B clutch, or holding it in the counterclockwise direction with the one-way clutch. Then we add the clutch container. A lot of people like to refer to this as the trash can. How disrespectful. This is such a nice piece of machinery. I could just imagine the machinist that's pumping these out, realizing that the whole world is calling this a trash can. I hope he never finds out, but it would actually make a nice trash can, except for the hole in the bottom. Everything would come out. But anyway, so clutch container. It is, as it shows here in the picture, we've got the carrier up the front, F clutch splines to it in the middle, and then we have the internal gear in the back. And on that same P1 gear set, the internal gear assembly is going to have A clutch that's going to go around it, and it'll be able to lock that A clutch. The A clutch will be able to lock that P1 internal gear, ring gear, to the case. Then we got this hub assembly that goes in the middle, as I've showed you before. This hub assembly has the P2 ring gear and the P3 sun gear. Right? So that's a common connection. Our P3 carrier assembly, and you can see it splines to the C clutch. And lastly, we have our E-clutch drum with the P3 ring gear and the P4 sun gear. That is a common connection. Without me taking it off of the input shaft, just for the sake of showing it to you, you could see that that ring gear right there through this housing is connected to that sun gear. If I spin it, it's all the same. Now, it's not connected to the input shaft unless, as you can imagine, the E-clutch applies. Okay, so power flow, there's a lot going on here. So we're gonna kind of go through it. Don't blow out a brain vessel trying to figure it out, but the basic gear set rules still apply. You know, if you've got 2 parts input, you got direct drive. If you've got 1 part held and 1 part input, the third parts can be outputted at gear reduction, overdrive, or reverse. If you've got 2 parts held, then that gear set doesn't spin at all. And if you have an input or a held part, but not one of each, you've got neutral. So in this case, first gear, what we've got, so you can see the range reference chart is over there. So we have our A clutch applied. So what I did is I deleted the clutches that are not being used in those particular gears. So we have our A clutch applied, and we might have our B clutch applied. You know, that's what the asterisk means. But we definitely have the one-way roller clutch, and this sun gear is gonna have the tendency to spin counterclockwise, and that one-way clutch will prevent that. So basically, when you think about it, if I've got my A clutch holding my ring gear so it can't move, and my one-way clutch is holding the sun gear so it can't move, that carrier can't move. And if that carrier is splined all the way to the back to this internal gear, ring gear, whatever you want to call it, that's stationary. It cannot move. So this is our held part in first gear. And then if you remember, our input shaft, right? We got our carrier assembly right there. It's doing its thing. And, you know, so it is, if this is held and this is input as far as our first gear situation is, like our input shaft is going to be rotating, so it's going to be driving this carrier. Our sun gear is going to be held because it's held by the one-way clutch. That means this is going to spin in overdrive. Our ring gear / P3 sun gear is going to spin in overdrive. But if you look at this P3 gear set, there's nothing else going on. I'm not holding anything, and I'm not driving anything. So that means it's just kind of freewheeling. It's not doing anything. If I've got my E clutch applied, that input shaft is actually going to go through and drive this shell once again. So this, theoretically, this would be the input to the P3 gear set. That would be input. And the third part would be output, but there's no connection to anything, so it's not doing anything. So that's the reason why this P3 gear set is pretty much operating as if it was in neutral. So then when we look at our P4 gear set, it's being inputted. The sun gear is being driven input shaft speed. So we got our input shaft spinning. This gear set's really doing nothing. But back here, since the E clutch is applied, we're driving at input shaft speed. Our sun gear, ring gear's held, and the output shaft, which is always the carrier, is going to be the output. So a small gear driving a big gear, and that's the first gear ratio at 4.69 to 1. That's a low gear. So now if you take a look at what gear set's actually doing any work, yeah, these parts are spinning here in the P2 gear set, but there's no torque traveling through it. So it's not really loaded. So if you were worried about a noise situation or something, in first gear, you're really only going to have the P4 gear set transferring torque through it, which means your noise issues would be just the P4 gear set. So if you didn't hear it in first gear, it's probably the P1, P2, or P3 gear set. If you do hear it in first gear, pretty much got to be that gear set, right? Because that's the only one where torque's traveling through it. Good to know. Sounds like that could be a pretty good test question. So now we're in second gear. We've shifted the second, shift solenoids did their thing. Now pressure is being released from the, as you can see by our range reference chart, the E clutch gets released. So the solenoid takes the line pressure off the E clutch and gradually drops it off. And then our D clutch turns on. You can see our D clutch, which is right there, it turns on. So our shift solenoid is going to ramp up the pressure to the D clutch and give us a nice smooth shift. Now we do have this P3 planetary gear set doing something. If you maybe can guess, our P3 planetary gear set is locked to our hub assembly that is also our P2 ring gear and our P3 sun gear. So that means if our P3 carrier and our blue, the sun gear, are spinning the same speed, guess what that has to do? So these two are locked together. That means this one's locked together. So this whole middle section here is spinning at a slight overdrive, right? Because I've got my input shaft driving that carrier, and that carrier, whenever a carrier is input, overdrive must occur. And this is the internal gear, is the medium-sized gear, so the sun gear is still held stationary through the one-way clutch. And that means this carrier assembly is going to spin in a little bit of an overdrive. It's going to spin this sun gear a little bit faster. So that sun gear is going to spin faster, and that's going to carry this internal gear and maybe I'll say that better. So now here we are in second gear. We did this nice upshift where our computer went ahead and released the E clutch and applied the D clutch. Here's the D clutch. You can see the E clutch is no longer there. Disappeared. So that's the releasing clutch, and this is the applying clutch. The key factor on this one is by applying, because the C clutch was applied before in first gear, it just didn't do anything because there was nothing, it wasn't connecting anything to. There's nothing other than the shaft here that was connected to. So it was kind of a preparation really for this shift here. So now that we've got this D clutch applied, we are locking this P3 carrier to this, everything you see here in blue, which is the P2 ring gear and the P3 sun gear. And if the P3 sun gear and the P3 carrier are locked together, they've got to spin at the same speed, which means everything you see in pink has got to spin at this speed too. So this gear set is working in direct drive at this point. Hope you understand that, because it can't spin any different. If this clutch, if these two clutches are locking the sun gear and the carrier together, those two parts can't spin independent of each other. That means that ring gear is going to have to spin at the same speed as these two. You're like, well, wait a minute, did that really accomplish anything? Yes, it did. Because this P2 gear set, since that carrier is always input, that sun gear was held, I said that 5 times, that's all right, by the one-way clutch, that's going to force this ring gear to spin in an overdrive. So all these parts back here that are spinning at direct drive, the P2 gear set is feeding it in a slight overdrive. That's tricky. So this slight overdrive then is going to spin this rear sun gear, P4 sun gear, a little faster. So think about what happened. When we were in first gear, if we need to steal a little bit of that gear ratio away, so that way we can make the output shaft go a little bit faster or bring the input shaft speed down, I got 2 options. I could start spinning my ring gear clockwise. That'll steal a little bit of the gear ratio. Or I could start spinning my sun gear a little faster. Because this is in first gear, this is going input shaft speed. If I can overdrive this, I will then speed up or try to speed up my output shaft. And that is how they do it. So the shift is going to occur, the upshift and bringing the engine speed down. The goal is to bring the engine speed down or bring the output speed up. And the way they're going to do that is by either systematically spinning up our sun gear or spinning up the internal gear or ring gear. You're going to see that happening. Because right now this is still held stationary. This was going input shaft speed in first gear. Now it's going slightly faster than input shaft speed in second gear. And that's what forced the ratio to drop down to close to a 3-point. And that just took me 5 minutes to say what I have written down there in 4 little steps. Now for noise diagnosis, the active gear sets that we have is the P2 gear set for sure, because now this is working that overdrive. It's not a whole bunch of high RPM spinning. You would think that this P3 gear set, because it's active in a sense, but it's all spinning in direct drive. So there's no meshing going on. So we'd say, nah, there's really no noise concern or ability there. Now this P4 gear set, yeah, that's still going. As a matter of fact, pretty much all gears except 7th gear, there's going to be meshing going on in that P4 gear set. Now we're at 3rd gear. And 3rd gear, the tendency for this P1 sun gear is going to allow it to spin clockwise. So you can see the one-way roller clutch is now going to let it spin because it won't hold it in the clockwise direction. And that's a little trick too, by the way. If you're ever wondering which direction a roller is going to freewheel, realize that when this is in 7th gear and it's direct drive, all of these parts are going clockwise. So that means you can't have a one-way roller clutch holding something in the clockwise direction, at least if the types of roller clutches are going to be holding between the component and the transmission case. So with this arrangement of clutches, I've now got my P2 ring gear through the C clutch, through the D clutch, through that carrier assembly, and that, if you remember now, that carrier and that sun gear are spinning the same speed, and since I have my E clutch applied, I'm locking the rear sun gear to this whole conglomeration of P2, P3, and now P4 gear sets. So that's all spinning input shaft speed. And when I did that, that carrier is now going to force this sun gear to spin clockwise, and that's what caused that roller clutch to freewheel. And by doing that, that actually is now causing this P1 carrier assembly to start rotating clockwise. And whoa, okay, so now we're getting there. First two gears, we were spinning the sun gear faster and faster, and now we're actually starting to spin my ring gear, my P4 ring gear faster, and that steals a little bit of that gear ratio. So we go from a 2.98 to a 2.14. That's our third gear. And as far as our active gear sets for noise complaints or noise concern, P1 gear set, it's now doing some action there. We've got some meshing going on there. So if you just start to hear a noise when it hits third, wasn't there in first and second, well, look close to that P1 gear set, and we have our P4. The reason why the P2 gear set and the P3 gear set aren't responsible for or potentially making noise is because these are all spinning at input shaft speed. It's all like a direct drive. So this middle gear set's working direct drive. All the work's being done meshing-wise by the front and the rear gear set, P1 and P4. All right, so fourth gear, a lot of stuff going on here. Starting to get a little clustered, but I think we can figure it out. So we have our A clutch, F clutch, C clutch, and D clutch applied. What happened in this shift is our E clutch turned off and our F clutch turned on. So you're like, what's being accomplished here? Well, by having the D clutch and the C clutch on at the same time, we're forcing this P3 gear set to spin in a direct drive because we're locking the P3 carrier and the P3 sun gear at the same speed. So this whole gear set right here is working in like a direct drive, which means that's connected to the P4 sun. You're like, wait a minute, isn't that what it was doing the last gear? Kind of. But here in this P2 gear set, we are driving this at an overdrive because the sun gear is going to be reacting off of that stationary ring gear, and it's going to be rotating clockwise a little bit faster, and that is going to drive this P2 ring gear and this whole connection here of P3 gear set and P4 sun in an overdrive, and that's going to be our shift. We're going to drop it down from a 214 to a 276, and we've got fourth gear. Feeling pretty proud of that. And so far as like what gears are meshing, which gears are actively meshing, so the point where if I've got a noise diagnostic concern, what do I need to look at? Well, basically in fourth gear, we've got our P1, P2, and P4. Like I said, P4, always going to do it except for seventh. That's direct drive for this whole gear set, so there's no meshing going on in any of the gears. But we have meshing going on in the P1 and the P2 gear set, and then we have a direct drive action that's occurring in our P3. And now we're halfway there. We're at fifth gear. So what happened in fifth gear? We still have our A clutch applied, our F clutch is still applied, our C clutch is still applied, our D clutch turned off. Our D clutch turned off and our E clutch turned on. And we know what happens when our E clutch turns on is now that P4 sun gear is going input shaft speed. So if it's going input shaft speed, what's going on with this P3 gear set? Well, absolutely nothing, because once that C clutch or D clutch released, you can see I have an input and I have an output, but I have nothing's going on with this third gear set part. So it's acting just like it's in neutral. So this is just idling along. You're like, well, okay, well, what's really happening now then? Well, our F clutch is applied and our C clutch is still applied. And if this is working at an overdrive, because, you know, we've got a carrier as being input, this isn't held, but it's moving, it's reacting. It's kind of like, call it a moving reaction part. And that is going to be directly connected and feeding into this P1 carrier, clutch container, and then ring gear. And that whole action there is going to force this rear ring gear or the P4 ring gear to spin a little bit faster. It's going to take our gear ratio from 176 to 152. And that is our 4-5 shift. As far as meshing and actions going on, just like the last gear, we have P1, P2, and P4. P3, spinning. These parts are always kind of meshing, but there's no torque being transferred through the P3 gear set. And now we shift in this 6. And you can see here, A clutch is still applied, kind of looking for a break. It's been on pretty much this whole time, so just saying. Almost at the end of its shift though, literally, no pun intended. So the F clutch is applied, the D clutch is applied, and our E clutch is applied. So in this gear, because the E clutch is applied, we know our P4 sun gear is going input shaft speed. But connected to that whole assembly, that whole drum assembly, is our P3 internal gear. So our P3 internal gear is going input shaft speed. Our center, this blue hub assembly that connects the P3 sun gear and the P2 ring gear together, it's going to react off of the carrier assembly that is connected through the D clutch to the F clutch to change the speed of our rear ring gear, our P4 ring gear, to get the gear ratio to drop from a 1.52 to a 1.27 to 1. And in this case, all the gear sets are active. There's meshing and torque being transferred through every one of those things. So if you have a noise concern, 6 gears probably not going to be the one to help you because it could be any one of the 4. So now when you shift in the 7th, if you thought you had a gear set noise and you shift in the 7th and you still hear it, it's not a gear set noise. It's a torque converter, oil pump, something else, engine, transfer case, some other issue is going on. So that's actually a good little hint there or tip if you're diagnosing a gear noise concern. Because this whole assembly, by turning off our A clutch and applying our F, C, D, and E clutch, we're basically forcing all of these parts to spin as a unit. So this is going to spin as a complete block of metal, and there's going to be no gear meshing. So you can see right there, it's 1-to-1. And what happened when we did that, we saw our A clutch release and our C clutch apply. So now here we are in 8th gear, and the B clutch can finally turn on. You can see it looked like it was forgotten there. It hadn't been used in a long time. It was being missed, but now it's back. B clutch applies, and what the B clutch does is it goes through and it locks our sun gears, the P1 and the P2 sun gears. By doing that, now I've forced this middle gear set to work in a overdrive. You see what happens here is carrier is input, overdrive must occur. So the carrier is input, sun gear is held. That forces this, the P2 ring gear and the P3 sun gear to spin in an overdrive. And you're like, all right, overdrive, that's good. Now the P3 ring gear and the P4 sun gear, since the E clutch is applied, it's going input shaft speed. So this E clutch forces all this to spin input shaft speed. So I have an overdriven sun gear and an input shaft driven internal gear or ring gear. That's going to cause a slight overdrive that's going to occur with my P3 carrier. So that slight overdrive is going to come around and drive that ring gear here, the P4 ring gear, a little bit faster than input shaft speed. This is going input shaft speed, that's slightly faster than input shaft speed. That gives our carrier an overdrive, and that is our first overdrive. Congratulations, you just made it to the 0.85 overdrive, and you should be proud of yourself. And our active gear sets are the P2 gear set, P3, and P4. The P1 gear set isn't doing anything. It's spinning, it's meshing, but there's no torque transferring through it because there's an input and there's an output, but there's nothing held or no other second input. The A clutch is released. Now we shift into 9th gear. We're like, okay, well, what they did here is they released the D clutch and now applied the C clutch. So instead of letting this carrier slightly spin in an overdrive, they're going to use the full overdrive by having a sun gear that's stationary, carrier that's input, and an overdriven internal gear go straight up and drive this P4 ring gear at an overdrive, a greater overdrive than it had in 8th gear. And now only the P2 and the P4 gear set are meshing and delivering torque. And now here we are in 10th gear. You've made it to the end, but we're not done. There's still reverse. Gotcha. But what happened in 10th gear? The E clutch turned off and the D clutch turned back on. And the main accomplish here, what they're trying to accomplish here is we know we could spin this at an overdrive, but now we can also spin our sun gear because the E clutch is off and it's not going to lock that rear sun gear at input shaft speed. They'll be able to overdrive it a little bit. So overdriven, get you the good 0.63 to 1. That's the gear ratio for fuel economy right there. So really the P2 and the P4 gear sets are the only thing that's delivering any torque and meshing at the same time. And the reason why is because that P3 carrier is connected to the P3 Sun gear. So this middle gear set's actually working in direct drive. But because of the overdrive that's occurring from our P2 gear set, it's not only driving our clutch container and P4 ring gear, but also this whole triple clutch housing along with the P4 Sun gear spinning in overdrive. So that naturally gives us the best overdrive that we can get, and that's our 10th gear. So finally, this is the last one on PowerFlow, reverse. I won't trick you with anything else. But if you remember what needs to happen for reverse to occur is we need to have a carrier at some point causing, usually you hold a carrier to get a reaction that occurs. Now, we only have two holding clutches. We have our A and B clutches up here. But they can actually get that to happen because if they lock this front gear setup, which they're doing, by the B clutch holding the Sun gears and the A clutch holding the ring gear, they've effectively held this the trash can, I almost said that, clutch container stationary. And then if we apply our F clutch and our D clutch, looky there, we're holding, these engineers, they're so smart, they're holding the carrier stationary. So now my input is going to come in with a carrier being held stationary and an input from a Sun gear. We're going to have a medium-sized gear, or the internal gear is going to spin in a reverse rotation. The reverse rotation on the P4 Sun and our ring gear assembly is still being held stationary because of all that good stuff up front, and we get our output shaft to spin in reverse. Simple as that. I could have come up with this. No way. This is actually pretty impressive. So just to recap on that mechanical stuff, here's our range reference chart once again, clutches and solenoids, and this is like a noise chart. These are the gears that are meshing while you're in those particular gears. You can remember 7th doesn't have anything, and first gear only has P4. But all the others have multiple gear sets meshing, so that might help you trying to diagnose gear noise. Especially if, like, for example, you're having only noise that's occurring 3rd through 6th. You don't hear it in reverse 1st and 2nd, and then after 6th gear you don't hear it, probably got something going on with the P1. Or if you're always hearing a noise except for 7th, P4. If you're always hearing a noise, even including 7th, probably not your gear sets. It's gotta be something else. So anyway, that could be helpful. You're welcome. So now we're going to jump into the hydraulic operation. We're going to look at these three main subjects. The line pressure control, a little different from what a typical GM Ford transmission uses. We're going to look at their linear solenoid operation. That is something that's truly different from what they've done in the past. And then look at their torque converter control. There's a few things with that, like the priority valve. Now, if you watched the torque converter video already, you will have noticed that the torque converter Generation 1 versus Generation 2, GM, it did change its design, but really the operation of the torque converter, the operation of the hydraulics is pretty much the same. They just have to change which passage the applied pressure goes through, but the concept is still the same. So to talk about the hydraulics, I'm going to focus primarily on the GM system because they're pretty much the same as the Ford. They collaborated and came up with this design. And right here, main regulator valve, the variable output pump, the variable force solenoid, which is normally high, basically the line pressure solenoid. They use this thing called the isolator valves, these tiny little accumulators or dampeners. They're in there. And they have this thing called an anti-backflow valve, and it's really a start-stop thing. And oh my goodness, my head dissolves into the graphic. Goodness. Look at it's like, that's how much I listen to transmissions. You could see the pump working in my brain. So the fluid pump assembly, if you remember from the intro videos, the variable output pump, that's what this thing works off of. So it's going to use the premise. There's a priming spring, and this little candy cane striped pressure passage is the decrease pressure. So when this pump generates enough pressure and that line pressure finds its way over and starts compressing this spring, and when it can overcome the tension of this spring, plus whatever any additional pressure the line pressure solenoid creates, it will eventually uncover this decreased passage. So some of that line pressure will find its way into that decreased passage. And when that pressure builds up, it's going to get trapped between that little pivot pin and the seal right there. And it's going to cause this whole slide assembly. Get my fingers right. It's going to cause that whole slide assembly to kind of pivot around. So that slide's going to compress the spring and pivot around, because what's happening right now is these little paddle wheels, those rotor vanes that they call them, when they're sitting there rotating, they're sucking fluid in through here. So that's suction, and it's compressing fluid out. So it sucks it in through a low pressure. So by this opening expanding right there, it creates a low pressure, and that draws fluid in from the pan. You can see it's like, finds its way up, defies gravity, lower pressure in that pump will draw that fluid in, and then it carries it around and then squishes it out, and then that fluid pressure finds its way out. It's off the screen and comes down and goes back over. Not only does it feed all the hydraulics and with line pressure, but it also works against this regulator valve. And the surface area difference, you can see I got a small surface area here, a larger surface area there. So the pressure that's in here is going to exert a force and move that valve over that way because of the greater surface area on this side than there is on this side. That's the different. Now, like in here in the middle, the spacing is the same, so fluid pressure in here doesn't act on the valve. Fluid pressure on this side, which comes from the solenoid, follow it down. So the line pressure coming in, the solenoid modulates some kind of pressure, whatever it feels it needs, into here. That adds to the tension of the spring to keep the valve shuttled to the right. And then that line pressure builds up and pushes that valve over to the left. And when you finally get to the pressure that it wants, that pressure ekes into this decrease passage. And as I just got done saying, kind of at the beginning of this super long run-on sentence, it works against this pump slide, moves it over, compressing that spring. That equalizes the space around this paddle wheel. And then you can't create as good of a low pressure. That means you can't suck that much fluid in. If you can't suck something in, you can't squeeze it out. And there you have it. That's the pump in a nutshell. That's how that main regulator valve works, right there. Balancing line pressure on this side with that spring and solenoid pressure on this side with that spring right there. This is the variable force solenoid. That's what VFS stands for. It's a line pressure solenoid. It's taking line pressure in, which is different from earlier transmissions that were fed a solenoid feed or a module, like a lower, they call it AFL, actuator feed, a little lower pressure. But this will actually receive line pressure. And then as they pulse width modulate this, the more they turn this solenoid off, the more pressure it lets through. That's the reason why over here you can see VFS NH, normally high. That means electrically off, it passes pressure. Turn it on, it's about 1.1 amp or so, it'll block it off. So when there's duty cycled on, no fluid pressure gets through here. And if there's no fluid pressure gets through here, all it has to overcome is the spring, and it would be very low pressure. I'm going to guess, I haven't calculated it, but I'm going to guess like 30 or 40 psi. And then that'll open up the decreased passage. But then the more they turn this solenoid off electrically, pass less current through it by duty cycling the ground off more. And, so that it's not being energized. That's going to allow more fluid to pass through, and that's going to add to the spring. So now line pressure is going to have to overcome not only the spring, but also that additional pressure. And that's going to cause a lot more pressure, line pressure, to be developed before it moves this valve over enough to cut off or to decrease the pump output. And that could be well over 300 psi. A lot of pressure. This isolator valve is there to dampen the action and the reaction that's going on with that solenoid. Think of it as a miniature little solenoid accumulator. And lastly, we have this anti-backflow valve. And that has to do with the fact that we have this electronic start, stop, stop, start, however you want to call it, e-pump. So when you drive and you come to a stop and your engine shuts off, you lose your pump output because that's driven by the engine. And then, through the torque converter and through gears and all that stuff. And now they energize this electronic pump, and that's going to start generating pressure. I don't know why they got the arrows going that way, but so that pressure that it generates is going to keep the hydraulic circuits filled up. It's not going to provide you with 100 psi pressure, but it's going to keep them filled up. But what they don't want is all that volume to just backfeed and then leak out. So they have this anti-backflow valve. So if the pressure drops off, we don't have line pressure anymore feeding the solenoid because the pump shut off. So if I don't have line pressure feeding the pump, and that means I don't have any pressure on this side of the valve, well, this spring right here is going to move it over and it's going to block that passageway off and it's going to keep that line pressure circuit from draining back. Thus the term anti-backflow valve or drain back, I don't know, but yeah. Okay, so on this slide, I just want to throw this in there for you. This is just a little experiment that I have out here, as you might know. I've got a bunch of pressure transducers tapped into this 10-speed transmission, measuring the actual clutch pressures. I also check line pressure, and you can see this top one right here, which is like a dark red. At least it is to me. I don't know what you see, but that is line pressure. And you can see how active it is. Right here, like in the first gear and then the 1-2 shift, is about 40% throttle. I'm at about 190 PSI. That's where that would be, about right there. And you can see the clutch pressures are pretty close to that. And they pretty much, any clutch that's applied closely follows that line pressure. Then right after the 1-2 shift, it drops off. And then you can see it just kind of, it's active. It's moving up and down during, like this is between the 3-4 shift. You can see it jumps up during the shift, and it jumps back, or drops back down. And then didn't seem to care about the 4-5, about jumping up too much. Actually lowered on the 5-6, and then lowered a lot, and then said, oh no, we're gonna do the 6-7, better boost it, we're right back up. And mind you, that was all holding the throttle completely steady. So the computer's doing a lot in the background. And how's it doing that? It's changing the current flow through the solenoid, and it's changing the current flow by changing the duty cycle of the solenoid. And the more they turn it off, the higher the pressure. The more they turn it on, the lower the pressure. Now moving over to the shift solenoids, these are CDAS solenoids. I like to call them linear solenoids, so I don't have to say CDAS all the time. Casting integrated direct acting solenoids. And that just means that instead of controlling hydraulic pressure like a lot of like the line pressure and the torque converter clutch solenoids do, what this is actually doing, it's got a little pintle that physically pushes on the valve. I'll show that to you here in a second. And it's nothing new. Honda's been doing it for a long time with their CPC solenoids. Toyota's been doing it for a long time. But as far as GM and Ford's concerned, as far as I know, this is something new that they just have gotten into. And another thing that's kind of interesting is in the valve body, the valve that this is working up against is not returned or held to this with a little spring. They're actually using pressure, they call backfill pressure, to keep the valve kind of pressed up against the pintle assembly. So no springs. And I just want to show you this because something to think about. It's like more speeds, the better, right? Well, realize this. Every one of these little areas here is the shift. So this is me, this is a 10-second acceleration. If you look at the timestamp down there, it's like, I don't know, a little over 4 seconds. And then this is just the 7th gear, and I'm 10 seconds in. And that's the amount of time it took to shift. 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7. So in between those is while you're in a gear. I'm in the gear, in-gear situations, or in-gear moments. Spending most of the time shifting. So you're like, oh, well, whoop-de-doo, what's the big deal? Well, they actually pull quite a bit of torque during the shift. So you can see right here, this is the shift. RPM's dropping every time it shifts. This is the shift command, step, 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 step. And then that's the vehicle speed, has him going a little faster. And then over here, this is the actually calculated engine torque. And how they reduce that engine torque is by, in green, the spark timing. You can see it drops. It's like, wait, that goes below. If I go over here, that's 0. So it's actually on the 1-2 shift and the 2-3 shift, it actually went to after top dead center. That's how much timing it pulled, which is insane. So you can see the average timing during that acceleration was probably maybe 15 to 18 to 20 degrees. It almost pulled all of that out. It actually pulled all of it out and went after top dead center on the first 2 shifts. Another thing that's pretty wild is on the 1-2 shift, not only is it reducing torque, but look what it did. While throttle is being held, 50% throttle in this case, while throttle is being held pretty steady, so that was 50% throttle right where this line is, Look what it was doing, or I should say accelerator pedal was being held stationary. Look what it's doing to the throttle the whole time. It's all over the place. It's not staying at 50 or anywhere close. It's moving it quite a bit. A very active unit, changing line pressure, changing throttle position, changing timing, all this in the name of torque management so that the clutches survive during the shift. So this is what a shift actually looks like. So this is scanner data, and it's from HP Tuners. They got a really nice scanner function. This clutch right here is the releasing clutch, and this is the applying clutch. It could be any clutch. It really doesn't make a difference. And in this case, I'm releasing the D clutch and I'm applying the C clutch. And this is really a topic for a completely different lesson, but just to let you know, there's 4 phases of a shift. Phase A is the fill phase. So they're going to drop the releasing clutch, not completely release it, but just kind of drop the pressure to a manageable level. And then while they're doing that, they're actually filling the clutch circuit up for the applying clutch. Then they have this B phase, which is called the torque phase. And this is where the handoff occurs. So they drop the pressure completely on the releasing clutch, and then they start applying pressure on the applying clutch. And there's no ratio change that's occurring at this point. If you look, this was engine speed dropping. You can see the engine speed did not drop during that phase at all, because what they're doing is they're handing off kind of the responsibility from the releasing clutch to the applying clutch. They call this a torque hole, because there's like not much being accomplished in this phase. And then this is the inertia phase. The inertia phase is where the shift occurs. So this whole sequence right there, that's your shift time. That's what you feel. And that's happening during phase C. And then once they feel the shift is complete, they bump you up the line pressure. And if you look, this is the actual same shift recorded at the same time, and they look really close to the same. You can even see that little hump right there. That little hump right there. You can see the fill pressure went up and then dropped down, then it went up again. Went up, dropped down, went up again. A little more dramatic looking here, but that's probably just the vertical scaling. If you put the numbers up there, they basically say when this thing's sitting there in a steady state operation, you're in gear, that you have 310 PSI. You don't have anywhere near that, like ever. So, but when it drops down, that releasing clutch drops down to 75 PSI, then kind of drops off. And then the applying clutch goes up to 20 to 30 PSI. This is all data that the scanner was displaying. You can kind of see a little bit, that's the legend on the side. And then it brings it up gingerly and then goes back up to 310. Well, it actually was about 75 PSI according to the pressure transducers. See, that says 83, so 75 was probably pretty close to that. Then it dropped it all the way off. And it probably did go from 20 down here during the fill phase, 20 at the fill phase, and climbed up to about 35. And then that was about 35. So what I did is I moved the vertical ruler and measured what the actual value was. And the point of this is showing that the scan data and the reported pressure that they have on it is actually really close to the transmission. Now, mind you, this transmission was perfectly fine, so I wasn't really trying to diagnose an issue. So this could be commanding these pressures but not getting them. So you can't trust this as if this is actual pressure. That's just the solenoid command, that's what they want. But they actually got what they want. And I feel like that was pretty cool, pretty impressive. Just realize that it says 315 when you're in a gear, you don't get 315. In this case, this is just less than 100 PSI. And that's why so much of a dramatic climb right there, and you don't really have that dramatic of a climb going on the actual pressures. So knowing how precise the electronic control is with those CDOS solenoids, linear solenoids, and the line pressure and the throttle manipulation, when you're rebuilding this thing, keep in mind your clutch pack clearances. So you got all these clutch pack specs, and most of these specs exist, I mean, from minimum to maximum, 12 to 24 thousandths, 12 thousandths to 24 thousandths window. And then they have all these different options for adjusting that. They got 5 plates for the A clutch, 6 snap rings for the B, 5 snap rings, and so forth. And they really change between, let's just say 8 thousandths of an inch for each different part number. So you can kind of tweak and get those clutch clearances where they need to be. So you want to do that because this thing has such precise control over it. If this piston's having to travel too far, or if it's too tight, doesn't have to travel that far at all, then you can run into problems because they're always purging air. You can see this is just, it's sitting there running, and this is switching between the F clutch and the D clutch, F, D, F, D, and then that pressure is about 18 PSI, and that's a lot of pressure. So if you have it actually might be moving that clutch a little bit when it's doing this air purge, and if your clutch back clearance is too tight, you might actually feel that little nibble. So that would be bad. You wouldn't want to do that. That's actually a picture of the transmission. I put all the transducers on, in case you were wondering. More air purge that's going on. This is the A clutch and the C clutch. Okay, now we're going to look at how these linear solenoids do their thing. And there's 2 generations, and it's not too complicated. I think you're going to like it. This is pretty cool stuff. If you're like me, which you probably aren't, you'll look at this and say, that's neat. Who came up with this? But 2 situations here. This is when the valve is off, and this is when the valve is on. So you can see the backfill pressure is pushing this regulator valve, they call it a regulator valve, flush with the solenoid. And then when they turn the solenoid on, you can see the little pintle come out of there and little finger just pushing on the end of that valve, and it moves it over. So we have line pressure coming in, and it can't go anywhere. These 2 spools are the same size, so there's no pressure movement, there's no movement on that valve at all, and this exhaust backfill is keeping it shoved over. Now when they start duty cycling the solenoid, and all these solenoids, when they're off, and when they turn them on, they push their pintle out. So when they're pushing the pintle out, they're going to feed this line pressure into the circuit. And what that pressure is going to do is it's going to find its way over to this clutch regulator valve. So we've got linear solenoid controlling the position of this clutch regulator valve that directs line pressure pretty much between 0 and whatever line pressure is over to this clutch regulator valve. And as that pressure builds up, it's going to move this valve over, let line pressure into the clutch circuit. And there you have it. Simple as it can be. If you notice, no accumulators, no dampeners, no nothing. So this thing, they're letting the fact that the linear valve is so smooth that it can control the pressures nice and smooth. And it does, as you can see in those pressure graphs that we just saw a little bit ago. Now the Gen 2 GM's got to do something a little different. They always got to say, well, this was working, but it's not working. It's working too good. We got to do something to mess it up. So they actually changed it around. And if you see, we don't have that second clutch regulator valve anymore. We're basically accomplishing most of that, or pretty much everything now through that one valve that's right off of the solenoid. And this is this F solenoid, just like in the F clutch, just like the Gen 1 is. So we still have line pressure coming in. When that linear solenoid pushes out, we're going to direct line pressure into these circuits. And it's going to go through this thing. It's going to find its way over to the clutch assembly. And you're like, wow, okay, they just eliminated a valve. That's actually better. But what they did when they eliminated the valve, they added this thing called a boost ball circuit. And this boost ball circuit, the way they have the schematic drawn, does not do it justice, because this boost ball circuit is basically going to, once there's enough pressure in there to unseat this check ball, the blue pressure that you see is going to find its way in there and move the valve over so that way we get full line pressure to that clutch real quick. And the way they do that, and they have 2 clutches that are being fed off of what they call feed limit low, which, as its name implied, is basically just going to have around 100 PSI pressure. And then they're going to have 2 separate clutch assemblies that are going to be working off their feed limit high. Now this one right here, being the F clutch, you can see it's plumbed to the feed limit high. So the F clutch is going to work off like 140, 150 PSI. So once line pressure overcomes that, it'll unseat that check ball, and the volume of fluid that will be able to find its way in here will help that valve move over quicker and build it up to line pressure. So to look at it, actually doesn't seem that complicated, and I guess it's not. When you've got fluid pressure coming in, and when that pintle comes out, it'll allow, as I just said, that fluid pressure to find its way over and then right into the clutch assembly. And they also have these orifices. So we have this orifice right here, and this check ball, and this orifice is what they call a triple orifice. There's actually 3 holes drilled, I'll show that here in a second, but basically that's what limits how quickly fluid can get in here to react off of this valve, because these two valve lands have different surface areas. And once the pressure does climb high enough and this check ball comes off the seat, the fluid from this side can fill the circuit quicker and cause the valve to react faster and not have to deal with the orifices that are actually pretty small up there. Now moving on to the torque converter. If you remember from the torque converter video that this thing has a unique torque converter, you probably remember that also from the intro videos, that this is the engine side, this is the transmission side. This would be the impeller, that'd be the turbine, that'd be the stator, and the converter clutch, these are dampening springs, the converter clutch is actually built onto a little turbine. And unlike most torque converters, it actually moves towards the transmission and applies against this tapered cover. It's kind of a neat design, but of course, GM being GM, they switched that, and now their second generation uses more of a conventional, I wouldn't say it's conventional, but they don't use this design anymore. But the first generation did, and Ford still does, so it's still a popular setup. And the way it operates is kind of straightforward, not too crazy. We have our line pressure feeding this torque converter solenoid. And then the pressure coming out of that, as they duty cycle that solenoid on, they'll deliver this torque converter signal pressure. And when that fills in this area, because of the surface area difference between this part right there and that part right there, it's going to shuttle this valve over to the left as you see it. And the line pressure coming in is going to change into torque converter clutch apply. And if we follow that down and back and up, it fills this whole section with line pressure, and that moves that piston and applies it against the cover, and you get lockup. Like, wow, easy as can be. It's great. Now this right here is a priority valve. You remember when we talked about the decrease pressure from the oil pump? Well, that comes into play here. That's why it says decrease right there. So decrease pressure will cause the pump to reduce output. So whenever there's decreased pressure, you know that there's more than enough pressure, that pump can deliver more than enough volume and pressure to satisfy the transmission, because it's saying, hey, tone it back a little bit there, buddy. You got too much pressure. So if you have decreased pressure, that means we have adequate output of our pump. If we don't have any decreased pressure, that means the pump is working at maximum output that it can and there's no extra. Well, so what they've done is they've created this priority valve and said, you know what, we can starve the torque converter of some fluid if we need to, because this thing, you can imagine there's going to be a lot of fluid kind of cycling through this converter. So instead of letting line pressure be low and cycle a lot of fluid through the converter and maybe burn up a clutch, they say let's starve the converter for a little bit and we'll let pressure build up. So if there's no decreased pressure, meaning the pump has not built up its max output yet, there'll be no pressure in here. This valve will move over to the right. If that valve moves over to the right, it blocks off this little passage. So line pressure cannot get into the converter feed circuit. No feed, no output. So that's why it's called a priority valve. They say the priority is going to be the line pressure and not the converter. So this, in a sense, is kind of independent of that because it just happens to be along the same line there, but it's cutting off that line pressure. Now in the second generation, they're still using the priority valve, and it's right down here, same spot. And you can see that's the decreased pressure. It's still there. And if there's no pressure at the decrease, meaning that we don't have max output of the pump yet, we want more pressure than the pump's delivering, this valve is going to move over to the right. If it moves to the right, now you're not feeding the converter anymore. Now let's just assume that everything's doing fine. We got decrease, our pump's doing everything it needs to do. Now we actually have converter feed. You can see the pressure comes in. In this case, it's finding its way there, coming around here, finding its way up into the converter. This is the release position. You can see the arrows right there. It's showing that the fluid's entering in here, and that would push the piston away from the converter. If you don't remember, since this is the second generation one, this would be the impeller side, that'd be the turbine side, this would be the converter clutch right here, and then the stator would be right there. So that fluid, as it feeds back out, It's going to find its way around, and it's going to find its way into the cooler circuit and lube circuit and all that stuff. But when they apply the torque converter clutch, what will end up happening is the solenoid, I don't have a drawing up here for you, but that's okay. You can see that pressure would come in right through here. It'd go down, it'd work off the end of that valve just like it did on generation 1. It would move this valve over, and now it would let line pressure find its way right on in. So it would go this direction, the opposite of those arrows. It would get on this side of the piston and push that piston up against the cover, and bam, torque converter clutch lock up. Hopefully it doesn't bang in the lockup, but anyway, so torque converter regulator controls the pressure applying the torque converter clutch. The torque converter clutch solenoid is going to manipulate the position of that valve. The priority valve is going to prioritize the line pressure over the torque converter clutch pressure, and if the torque converter clutch pressure, if there's decreased pressure, then it'll open up the passageway so that way you can feed the torque converter circuits. That's how that works. So as a summary, we went through the range reference chart and learned about all the clutches and the gears that they're used in. We looked at a bunch of common connections and went through power flow and all that stuff. We even did some noise diagnostics, kind of like figured out when these things might make noise and which gear set might be responsible. Then we covered some hydraulics. I mean, what else is there? It sounds like it's pretty complete.